Uh, Welcome back for the next session. In the first talk, we have R. Vijayaraghavan from the Tata Institute of Fundamental Research at Mumbai. He's going to talk to us about superconducting quantum electrical circuits. Vijay.
Yeah, thanks, MK. Good morning, everyone, and let me start by thanking the organizers for inviting me to this wonderful discussion meeting. It's a pleasure to be here, and as Peter mentioned, today it seems like the day for quantum information. And thanks, Peter, for including superconducting circuits in your esteemed team. I will try to actually address that point, why the superconducting platform became quite successful quite quickly. Hopefully you'll see it during the course of the talk. So I'm going to give a very broad overview of what this hardware platform is, what are some of its key achievements, and where the field is going. And towards the end, I'll say a little bit about the work going on in my own group at the Tata Institute of Fundamental Research in Mumbai. So let me start by just reviewing some very basic, which Peter, I think, already covered in his talk. Some very simplistic version of, Da Vincenzo criteria here. If you're trying to build any quantum computer or quantum information processing systems, you need quantum two-level systems, which become your qubits. You need the ability to create arbitrary states on them. You need to be able to measure the state very precisely during or after the computation. And then you have to create some kind of interaction between these qubits so that you can create entangled states. So if one puts this together, you can build a quantum information processing system. It's hard because qubits tend to be not very stable. In the sense that, if you prepare some quantum state, it doesn't remain there. And there are two sort of very basic processes. You have relaxation processes, which causes the excited state to come back to the ground state. And you have dephasing processes, which sort of affects the phase of your superposition. So if you create a particular superposition, say a block vector pointing in one direction on the block sphere, after some time, the vector could be pointing in some random direction. So you have this T1 time and T5 time of the dephasing time. This looks very pessimistic, but as was mentioned in the previous talk, a solution was proposed to use a collection of these imperfect qubits to still create an effective qubits. That's quantum error correction, and you can create logical qubits. And now we are really getting to a stage where these proof of principle experiments are getting quite good. We still don't really have a working quantum processor which uses these error-corrected qubits, but we are getting closer and closer to this milestone. So if you take a very simple view of what a quantum computer is, it's really just a network of physical qubits. You could have it in a linear array like that. So here the circles are meant to signify qubits. The red lines are meant to signify interactions between them. So how you lay out affects which qubits can talk to which qubits directly, right? So then you can have a square lattice. Again, just to repeat the same points, you need to be able to make local qubit operations, which means you have to be able to address any one of these n qubits and change their state. You have to be able to create entangling operations between pairs of qubits. Turns out that nearest neighbor coupling, like the one shown here, is sufficient. But if you had extended connectivity, which means that if somehow this qubit could directly interact with the qubit of the end, that can be useful in terms of simplifying the number of operations that actually takes place in the hardware. Here's an example of IBM's 127 qubit layout. You see that it's mostly a linear chain with a few cross links here. So these choices are made to balance out various challenges in a particular architecture. Some architectures like trapped ions and all naturally have all-to-all coupling, whereas planar circuit architectures like the superconducting qubits and others typically tend to have nearest neighbor coupling as well, right? So then you want to make measurements, again, on any of these qubits, and then you have to fight these two main challenges that you have this qubits being unstable, so you have finite quantum coherence. And also you want to be able to do this at a sufficiently large scale. A very small collection of qubits is not very useful in terms of using it for a practical application where it replaces current well-established techniques. So you need to build sufficiently large network to be able to, for it to be really useful. Okay, and there is a host of platforms you can build this. Essentially, you need a quantum two-level system. So trapped ions was discussed in the previous talk. Quantum dots, spin qubits in semiconductors will be discussed by David in the next talk. And I will talk about the superconducting circuit approach. And they're all equivalent in the sense that they implement an effective two-level system. There are many other platforms like photons, cold atoms, which are sort of variations of the trapped ions, topological qubits, NV centers in diamond. But currently, trapped ions and superconducting circuits are sort of at the forefront. Photonics is making a comeback in a big way in the recent years, and cold atoms has also done some pretty dramatic things, and they all have their own niches in terms of what kind of problems they are better at solving. Okay, so moving on, what is a superconducting qubit? It's easier to understand quantum levels in an ion or an atom. Quantum mechanics was sort of invented to explain what's happening at the atomic and photons, but one of the nice things or unique things about the superconducting circuit architecture that it's actually an electrical oscillator. And I've shown here a pendulum to sort of signify that one of the simplest qubit has the classical equivalent which looks like the pendulum, in the sense that it's a nonlinear oscillator, just like a pendulum really is, unlike what we learn in high school where we approximate the pendulum as a linear oscillator. So it's really an electrical circuit with just two components, an inductor and a capacitor. The inductor is actually made using a Josephson tunnel junction, which is what gives you nonlinearity. Here's a picture of one such device. The Josephson junctions are here at these intersections. It's essentially a sandwich of aluminum film, and there's a thin layer of aluminum oxide which acts like the tunnel barrier. You can look at some of the size scales here. There's the Josephson junction here. And if you look at the overall device, so that's now your inductive part, and these two big square things are your capacitors. This thing is almost a millimeter in size. You can see it with your naked eye. Not the Josephson junction, but for the full structure. But yet, it behaves like a quantum mechanical object under the right conditions. So the qubit here is nothing except that we're just using oscillations in the system with different energies. If the system is in the ground state or the oscillator has zero quanta, that's your qubit state 0. And the system excited to the minimum excitation allowed by quantum mechanics, which is 1 quanta of excitation in this oscillator, that's your state 1. That's it. It's one of the simplest designs, not one of the first ones to be invented in the field of superconducting circuits. And we will see a little bit later that there are other possibilities as well. Of course, there is always your 0-point fluctuations. You can also put all of this together on a chip. So this is a picture from one of IBM's chips. This is a 2-qubit system. So here is 1 qubit. The rectangular things are the capacitor pads. The Josephson junctions are in the middle. And then they are connected by these microwave transmission lines for coupling and measurement. So you can use standard lithography and fabrication techniques to make them. And that's one of the reasons why it has been possible to make complex chips today with thousands of qubits. Right? So a little bit more, you have your inductor and your capacitor. Here's a typical inductance and capacitance values. By having 2 junctions in a loop, you can actually tune the inductance by applying a magnetic flux. That's just a technical detail, but can be useful. Instead of a harmonic potential, you have a cosine potential, and that allows you to have these unequally spaced levels, and that's really why you can use this as an effective 2-level system, because the other levels are not on resonance, so you can isolate them, but it really is a multi-level system which you're using. And if you now operate at conditions where thermal energy is much smaller than 1 quanta of energy in the system, and typically these numbers are like this, about 5 gigahertz, which corresponds to 250 millikelvin in temperature units. And you operate in a dilution fridge at 10 millikelvin so that you ensure that thermal excitations don't mess with your quantum state, right? So you want the system to be found in the ground state after a sufficiently long wait time. That's sort of the assumption, one of the assumptions you make. If you operate at much higher temperatures, you will populate all these levels sort of in a Boltzmann distribution. And the reason for using superconductors is that it's one way of making electrical oscillators with very low dissipation or friction. An oscillating pendulum stops after some time. An excited oscillator comes back to the ground state. Just the same idea. So you want to minimize friction in the electrical language, that's resistance. So you try to make your inductors and your capacitors out of superconducting metals. You try to use the best materials to minimize any dissipation in the dielectric or in your surrounding. And that allows you, and there's been a lot of progress in the last 20 years or so since the first qubit, actually 25 years to the first qubit today. Peter had mentioned this in the context of including the superconducting qubit platform in the club of atomic physics systems, and that really comes from this architecture which was used to implement measurement. So you have your nonlinear oscillator here, as before, and now you couple that to a linear oscillator, now shown just with a linear inductor with some coupling capacitors, and this oscillator is coupled to the environment. This is exactly analogous to the cavity QED system where you put an atom inside a Fabry-Perot cavity. The Fabry-Perot cavity is your oscillator, here implemented as an LC circuit, and your atom is your two-level system, here implemented as a nonlinear oscillator. So this was given the nickname circuit QED because it's quantum electrodynamics, but in a circuit sort of architecture. And you use this in a very specific limit where the atomic resonance and the oscillator resonance are actually far detuned. And when you do that, the atom perturbatively affects the frequency of this cavity. So you have two resonance curves which depend on whether the nonlinear oscillator or the qubit is in the ground state or the excited state. And that becomes the basis for implementing a near ideal textbook quantum measurement, and I will address that a little bit later as well. So the basic idea is that cavity frequency depends on the qubit state, and the quantum state measurements are implemented by just sending a microwave frequency here and looking at two different values of phase shifts for the two different states. And if you can distinguish that, that implements a measurement here. Right. So once you have this, in order to control, since all of these oscillators are in the microwave regime, you basically control it by sending a pulse which is resonant with the 0-1 transition, like shown here. And you can do an experiment where you look at how the quantum state changes by having a pulse on the qubit followed by a measurement pulse and then varying the length of the time of this pulse. And you get this well-known Rabi oscillations, which essentially is telling you that the quantum state is oscillating on this Bloch sphere from ground to the excited state, back to the ground, and so on and so forth. If there was no decoherence, this would just be a constant amplitude sinusoidal wave, but because of decoherence, it slowly decays to a mixed state at very long times. Right? So this Rabi oscillation phenomena can actually be used for what are called single qubit gates to place the system at a particular point on the Bloch sphere. The amplitude of this pulse controls how fast these oscillations happen. Okay? The phase of this pulse, like whether at some arbitrary reference point looks like a sine omega t or a cosine omega t or something in between, it determines which axis along the Bloch sphere it actually rotates, right? So there's obviously no absolute phase reference. You have some reference point, and then relative to that, you can rotate it along different axes by controlling the phase of this microwave pulse. And the amount of rotation allows you to basically stop where you want after you have implemented this pulse. So using these three ideas, you can actually place the qubit. If you know the initial starting point, you can go from there to any other point on this Bloch sphere. And this is essentially what a single qubit gate is, ability to prepare arbitrary superposition states of a single qubit. Once you have that, you also need to be able to create interactions for entangling operations. Now, these are electrical systems. You have now two nonlinear oscillators. How do you make them interact? Well, you just connect them with some other electrical element. So, for example, a capacitor. So now this looks like a coupled oscillator problem. And under the right conditions, it can be used to create entangled states or superposition states involving multiple qubits with special things. Instead of a capacitor, as I shown earlier, you can also use a section of a microwave transmission line to create interactions between two qubits. In a very simplistic engineering sense, what you want is that the oscillating signal on a particular qubit should have a component showing up on another qubit. That's sort of a very simple way of saying what creating a coupling means in this architecture. So you can transmit that signal with the help of a capacitor, which typically means qubits have to be close to each other on a chip, or you can use this section of a transmission line, which is often called a bus cavity or a bus coupler. And that way you can now put qubits far apart, and that's critical if you're trying to build a large-scale chip so that you can lay them out quite nicely. Otherwise, you'll have to cram everything next to each other, and it won't work. Okay. You can also have other more complicated circuits. Now these plus things are the qubits, and this more complex circuits in the middle, also made of Josephson junctions, allows you to now actually turn the coupling on and off. Here, the coupling is sort of fixed by the design you have chosen, and here you can actually tune it by using these squids made out of Josephson junctions and applying local magnetic flux to turn the coupling on and on. Very roughly, the two big players in this field, IBM sort of went with this approach of fixed coupling architecture for most of the time till now, and Google went here, and Pedram is here. He probably talked more about this in his presentation earlier this week. But it looks like people are now going towards the tunable architecture, because when you have these fixed coupling architectures, you want the qubits only to interact when you want to do the 2-qubit gates. You would ideally like them to be idle at other times, but these architectures sort of achieve this in a special way, where when you're not doing anything, there is still some remnant coupling, and that accumulates errors as you go forward, and it becomes harder and harder, even though there's been a lot of new work in trying to address those situations, even in the fixed. So it's really a choice of technical complexity on how many components you want, how many control lines, versus solving other challenges in that which are sort of present in the Hamiltonian itself. So I'm sure we will see new ideas emerging for these as well in the future. The essential idea for doing this entangling gate or 2-qubit gate is that you want to make the evolution of one of the qubits depend on the state of the other qubit. So it's a conditional operation, and that's what allows you to create entanglement gates, and it's very critical. Without these operations, a collection of individual qubits is not very useful. Okay. So if I now summarize these points, the superconducting circuit has the ability to have tunable qubit frequency. You can have tunable coupling strengths. You can have localized high-fidelity control. You can implement high-fidelity measurement on each of the qubit. I haven't discussed that. I will say that in a little bit later. It all uses microwave drives. You can even engineer the baths, like the environment to which they're coupled in, by using appropriate circuits or additional driving. And you can really create customized Hamiltonians, right? I showed you just a simple oscillator, but what you have are these 3 building blocks. This image from the 2013 review by Devere and Sholkov shows that you have these 3 elements, and you can combine them to make any circuit. Each circuit will have a corresponding Hamiltonian, a corresponding energy profile for the potential well, and corresponding set of quantized energy states which you can use. And one of the first, and they have been sort of plotted on these 2 axes, where one axis is related to the shunt inductance, and the other axis is related to the shunt capacitance. And the qubit I showed you till now is the transmon qubit, which is just the oscillator, lies on this axis. But the Cooper pair box was sort of one of the first qubits which came up here. There are different parameter regimes which gives rise to different sensitivities to noise, easier control, easier measurement, coherence times, coupling to the environment. All of that can be changed. So in contrast to atomic systems, which are sort of fixed, and you just have to go with whatever is available and pick the best one, it works really well. Here you have the flexibility to design your own custom, effective atom. So that's why these were called artificial atoms. They have quantized energy level structures like an atom, but you can really construct them to your liking. In large-scale quantum processes, the transmon qubit is the one which is really being used, but the fluxonium qubit is emerging as a strong candidate, and there are some works for building processors using fluxonium. I think there's even a company which is trying to do that now, right? And it's really a combination of all of these things which really, I think, helped the superconducting platform move very quickly. And particularly the choice of frequencies, that is microwave frequency range, roughly in the 4 to 8 gigahertz. And the telecom industry had developed very high quality microwave instrumentation. And we could just take that and now customize them to get very, very good and robust control. And the ability to create different Hamiltonians allowed you to explore very different regimes, which were not so straightforward to do, for example, in conventional atomic systems. Okay. So I will now quickly go through some examples of some kind of things people have done with this. One of the applications of quantum computing is to do quantum chemistry. These are some early experiments using few qubits to just look at computing the lowest energy of very small molecules like hydrogen and lithium hydride using this variational quantum eigensolver techniques. The early results were good, modest. And then more recently, IBM has tried to use techniques to understand the noise in the system and then extrapolate the answers to get better results. And these have now improved to larger number of molecules as well. There are also other interesting experiments done, for example, modeling photosynthesis as an energy transfer problem by scaling the energy scales to make it relevant for the superconducting circuit. And this experiment sort of highlighted that noise actually was essential for the efficiency of this process. Right? So this gives some examples of simple modeling experiments you can do. The other big field which sort of set apart was quantum optics, and I think this is where one can compare with atomic physics, is because of the fact that the atomic physics guys had done all of these experiments in the past, we could go and run through them in a very short amount of time because of the much superior control at microwave frequencies and a much wider range of parameter space which we could access. So, in some early days, you could do things like looking at a nonlinear response of a vacuum Rabi resonance where you drive the system between two coupled systems, and you can get these extra features like the super splitting of each vacuum Rabi peak. More recently, you could also reach this beyond ultra strong coupling regime. So here is an oscillator, a qubit, a flux qubit, which is coupled to another oscillator here inductively, and they were able to engineer the parameters in such a way that the coupling strength, which is usually characterized by the avoided crossing or the splitting of the modes, is comparable or even larger than the frequency of the qubits itself. So that's also possible to achieve. These are much harder to do in conventional quantum optics systems. People have also used to study things like transport and localization in tight binding models. This is work from Will Oliver's group at MIT, doing quantum random walks, entanglement propagation in 2D lattice, and in various kinds of localization physics as well. Now, conventionally, because of the challenges in making qubits identical, because these are microfabricated, quantum simulations has typically been a realm of ion traps and cold atom kind of systems and maybe photonic systems. I think Peter gave some very nice examples in the previous talk. But there have been attempts here, and there are certain areas where disorder is acceptable. You can do some very nice things with these systems. And of course, with a approach towards universal quantum computer, you can program these things, which is now referred to as digital quantum simulation, and you can do very nice experiments if you have a sufficiently large and well-controlled quantum processor. I wanted to address this one other topic, which in the context of 100 years of quantum mechanics, quantum measurement has always been this mysterious thing. It still is. We don't really know why it works that way. As a student, when I started looking at these strong and weak measurements, it at least gave me a slightly improved picture, even though it doesn't solve the problem, on how measurement is happening. How do you understand this process of measurement in a system? And this is where the very textbook ideal Hamiltonian, which is possible in superconducting circuits, I think was very useful. So it's a reminder here, you have this qubit coupled to a cavity, you have two effective resonances, and if you shine light here and look at the measurement results, basically you get a phase. So consider this x-axis as the phase. And you see data for ground and excited states distribution, right? So it's a noisy measurement. You're measuring an analog phase. You will get a distribution, not exactly one value, which is what ideally you want. But if those distributions are very well separated, so here these are histograms of the ground and the excited state, and this is a log scale, so you see that the overlap is very, very small, so that the error is only a few percent, where the red curve goes below the blue curve and vice versa. And you also see there are these little bumps which tell you that the quantum systems are actually changing their state while the measurement is happening. Otherwise, it would just be two nice curves like shown in the dot dash line here. So this kind of very high quality measurement was possible starting maybe about 12 to 15 years ago using something called Josephson parametric amplifiers. And when you do that, you can now see these quantum state changes in real time. What I'm showing you is 6 different experiments, single shot experiments of measuring continuously the state of the quantum system, which is initially prepared in the excited state. And what you're seeing are these spontaneous emission events where the qubit decays to the ground state, stochastically at different random times. These are, of course, just 6 samples I have chosen, but you can see the quality of the signal and how clear and how easy this is. I think in the when Dave Wineland first did these experiments using the cycling transition, which Peter had mentioned, that was like a big thing because it was not believed that quantum jumps would ever be possible to witness. In fact, some people believed they were not real. And this was sort of done in superconducting qubits, I think back in 2012 or so. But if you take the same picture, what is this which is giving me this resolution? It's really this signal to noise ratio of this measurement to separate these two-phase histograms. Okay. If I now go to a different scenario where I prepare a qubit state and I send a much weaker pulse, like it's just the same microwave drive, I'm just reducing the amplitude. Okay. So I'm essentially making it difficult to measure that phase. Right? That in this picture is equivalent to saying that I actually don't have enough information to resolve the state of the two qubits, of the two states of the qubit. It's not because of technical reasons, it's because of fundamental reasons. Of course, you have to engineer the experiment to be in that regime. So if you do that, then these histograms may look highly overlapping. This is sort of partially overlapping, but if you make these two histograms overlap highly, then you don't really learn much. And that translates into saying that, okay, you actually not projected the qubit much as well. So this green curve is sort of a measurement obtained from the following strong measurement. So you prepare the qubit state, you do this partial measurement, and you will get some value in this range. It could either fall here or fall there. And what you see from the following measurement that if your initial result was towards this side, the following measurement projected it preferentially to that side. So if you think about a qubit in an equal superposition state in the middle, and then you did a weak measurement which indicated that the signal was slightly towards the ground state, then the following strong measurement verified that it was indeed closer to the ground state. So what really is happening in that sense is these weak measurements are pushing the qubit. It's sort of going towards the collapse, towards the eigenstates. So these experiments sort of tell you and you have a very nice and simple knob, which is you can understand what you're doing is that you're essentially limiting the amount of information you're extracting from the system. It's not just you, it's like nobody, the environment, the universe doesn't have any more information to extract from that. That's the condition in which you have to operate. And when you do that, you can get these quantum sort of trajectories. So each of these are with the qubit prepared in the equal superposition state. So the initial value is always at 0.5. And then they undergo these random thing and either end up at 1 or at 0 in this stochastic way, signifying collapse, right? So in that picture, a sequence of weak measurements, it's a strong measurement because each weak measurement gives you slightly more information and you push the system slightly more, but it's stochastic. It doesn't mean that once it starts going towards 0, it will keep going towards 0. It can also turn around, like, for example, this particular curve here. So it's random. The randomness here comes from the fact that I'm measuring a quadrature of my coherent state, and there is intrinsic uncertainty in knowing that, and that randomness gets translated to this random walk, and these were verified that, these are, of course, calculated probabilities by just looking at the weak measurement, but by using a carefully strong measurement and verifying the quantum state, as shown by these dashed lines here in these experiments by Cater-Mudge and all about 12 years ago, they verified that indeed the qubit evolves in this very random way by verifying, by doing quantum state tomography of the qubit at each of these points. So if you look at this picture, it really looks like this collapse is sort of a gradual process. Like in real world, no experiment is a measurement takes place in 0 time. So this, to me, it really was eye-opening as a student to sort of have this very simplistic picture which says, okay, I can now wrap my head around it. What is still missing in this picture is that this weak measurement still, at some point, you invoke a collapse on the coherent states being chosen by the environment to be one or the other. But in this case, you have many, many options. It's not a binary answer, but those binary those distributions gets clubbed into 2 different bins, which are corresponding to the 0 and 1 state. And there are other ways to do that, also using multiple qubits, but this is one of the ways. So I thought, in the context of the, celebrating 100 years of quantum mechanics, and of course these experiments are also done in optics and other systems, but I feel that this is one of the very clean systems where you can do that. So in the final few minutes, I'll just go through some other things. This whole idea of when quantum computers are going to become very useful, this idea of quantum advantage. Recently there was an experiment, again from the IBM group, where they claim that they can show some benefits in their 127 qubits, even before error correction is. There was this general idea that unless quantum error correction is implemented, you're never going to actually make a quantum computer do anything useful. People are still trying to use these non-error corrected systems to come up with some useful ideas. Then, of course, we had the whole quantum advantage debate, starting from 2019, where Google, with their 53-qubit system, performed this sort of constructed mathematical task called random circuit sampling, with this claim of 200 seconds for the quantum computer versus 10,000 years for the best classical supercomputer at that time. There was a follow-up result from China with slightly larger number of qubits with a different set of small and large numbers. And the most recent one from Google, of course, with 105 qubits, where the comparison is 5 minutes versus an insanely large number. But to me, and I think if you look at, if you suppress all the hype and look into the things the Google scientists are saying, to me the error correction result was, I think, a lot more significant. That this idea that you take bad things and you put more of them together and things get better. This was, I think, one of the first clean experiments which sort of showed that that is actually happening. Typically, you put more bad things and things get even worse. Error correction is supposed to be this magical thing where it's supposed to get better, and this was one of the first clean experiments, I think, which showed, and especially in the solid state platform. Okay. I will just very quickly mention, I don't think I have too much time, some of the things we have been doing in the last decade or so since the lab was started here in Mumbai. We've been looking at novel kinds of circuit ideas, sort of motivated from the fact that you have this nice building block of 3 circuits and you can put them together in various ways. So one of the first things we did was build a more complex circuit which has 3 different modes of oscillation. And 3 modes of oscillation at 3 different frequencies is 3 qubits. But it's a coupled system, so it really is like an effective 8-level Hilbert space. And we showed that it has the right structure to have universal control. And we ran some algorithms and showed that you can do it in much smaller number of steps, as opposed to the conventional approach of taking individual oscillators and weakly coupling them. So this was one of the things we did. Something we have done in the last few years was to address this idea of limitations in the planar connectivity, that typically if you put it in a square lattice, you have only nearest neighbor connection. We came up with this idea of using a circular transmission line and putting the qubits all around the periphery here. This is basically what's called as a ring resonator. And you get quasi all-to-all coupling while the qubits are still spaced nicely from each other to avoid crosstalk, and with reasonably uniform coupling. So we showed from calculations that if you have a 12-qubit system with 30-degree spacing at the right range of frequencies, each qubit is coupled to 9 other qubits and not to 2 other qubits. And this essentially can be understood by the fact that any signal from one qubit can either go clockwise or anti-clockwise to reach the other qubit. And depending on how they interfere, you get constructive or destructive interference that can give you zero coupling or high coupling. And you have to choose the angles and the things. And then we verified this using a 4-qubit system with the right angular spacing so that we could verify it for all the different angles for this thing. And it was done in this 3D circuit QED architecture with machined cavities and individual qubit chips. Currently, we are using this same idea to actually build a full 6-qubit quantum computer. This is really just to get our hands dirty on building a full system. It's not really a scalable architecture to build thousands of qubits. So we took this system, put 6 qubits with a connectivity which looks like this. You can see here, this is part of the ring cavity. This is the part of the readout resonator and the qubit sort of chips here. One of the advantages here is that it's a modular architecture. If one of the qubit is not working properly, I can actually just take it out and put a new one in, as opposed to replacing the entire chip in the conventional approach. This was done sort of based on what are the technical capabilities we had. And this is now being put together as a full system with all the software and the control electronics, and that eventually you'll be able to run a quantum circuit from a website and have it execute on this system. This is our first attempt in collaboration with DRDO and TCS to attempt at building these full systems so that we can go forward. I was asked to comment about other programs in India. You might have heard about the National Quantum Mission. So I'm leading one of the teams on superconducting qubits with 7 other scientists from 5 different institutes with sort of broad targets of getting to 24 qubits and 100 qubits in the next 5 to 6 years. We have a combination of superconducting experts, quantum error correction, quantum optimal control theorists, 3D IC experts, and control electronic expert, together with various central fabrication facilities which are also going to be set up, and collaboration with industry and startups as well. So with that, I'll end my talk, and I just place my summaries here. But essentially, the superconducting platform is a really flexible playground for doing all kinds of quantum experiments, and it sort of is one of the macroscopic quantum systems, if you would like. They're big in size, but under the right conditions, they behave quantum mechanically. And a lot of work has been done in pushing towards building a large-scale quantum computer, but I think there are still pushing the very same basic challenges, like if you could make the qubits better, everything will get easier. You need to figure out how to make electronics for thousands and millions of qubits not cost an arm and a leg, and then ultimately get to error correction for fault-tolerant quantum computer. Thank you.
Let's have a couple of questions.
Thank you for the nice talk.
Yeah.
I had one question, partly based on something I learned recently, that around 80s there was a parallel effort to develop superconducting classical computers, and they were based on SQUIDs and flux-based computing.
Rapid single flux quantum approach, yes.
Yeah, but apparently the time, among other issues, one issue was the time delay in readout and for classical bits. And do you think you have very fast, you showed timescales that are much better than in classical computers, but do you think eventually the same problem would appear on the superconducting quantum architecture?
No, I don't think at all. See, that's a very different problem you're solving. I don't agree with the fact that, in fact, superconducting qubits or any quantum computers, in terms of clock speed, like how fast they can execute, they're much slower than classical computers today. This is one of the challenges. They just live in different regimes. Ion trap and cold atoms operate very slowly, but they can work for longer, so you can get good number of operations. Superconducting qubits decohere very quickly, but you can also make them operate very fast, so you can get the same number of operations. I haven't done this comparison recently, but I think they're sort of similar in terms of how many coherent operations in a given, within the coherence time one can do. But the challenges for building a classical processor using this rapid single flux quantum logic and building a quantum computer is completely different. So there will be no such issues in terms of fast readout. So in fact, the qubit readouts are getting really, really good and fast. And that is not going to be the impediment anytime in the near future.
Okay. Thanks.
Hello. Hello, sir. Wonderful talk. The part on weak and strong measurements was eye-opening for me as well. But then another question popped up. in my mind, which I thought I should ask right now only. So the probability curves which you showed, which was gradually shifting towards that collapse, which we think is
Yes.
instantaneous. So that curve is the state of knowledge of the observer, or is it the qubit? It means, is it actually happening in the? Then you showed that those tomography curves, which showed the state of the qubit. But then the question shifts that is the quantum state represents the state of knowledge of the person, of the observer, or is it actually the thing which is happening inside?
So, see, these ideas are not platform dependent. If you want to put in the language you are talking about, these curves are calculated based on what we think, how quantum mechanics works, right? So in that sense, it's a inferred state of knowledge where we say that, okay, I knew that initially my quantum state was in an equal superposition state. That's a known thing because I prepared that state. And then by looking at the noisy signal I get from this weak measurement, I create these extrapolations, right? So that's sort of, you can say, a calculated state of knowledge. The measurements here, they then verify it, right? So it's a complicated experiment. You have to, because it's random, you cannot go back to the same state. So in order to measure the quantum state, all the three axes, you have to do what's called quantum state tomography, and it's an ensemble measurement. So when you have a deterministic state preparation, it's very easy to do. But here, this is deterministic, but after that, we don't know what's going to happen. So you have to very carefully, and it was done quite cleverly in this experiment, you choose the subset of results which give the same noisy signal, and then, or the same calculated final state, and you do tomography on those subset, and you see that the qubit is actually in that state. So you can say in that sense that using the weak measurement, you extrapolate your knowledge, but then you verify it with the strong measurement just to reconfirm that these are all the same.
Okay.
One last question.
Yeah. In your architecture, you said the 6-qubit architecture is not scalable. Can you elaborate? I mean, is it a structure, conceptual reason?
Oh, I just meant that if I want to extend this idea using machined cavities, then it's just huge. So I guess a size scale would have been used. So this square, it's about 5 inches or so. So a 6-qubit processor looks like a 5 by 5 inch, whereas IBM and Google's hundreds of qubit processors is much smaller than that. That's just because the microwave structure here is extended out for this modular nature. What I meant is that it's not possible or practical to build such a large system. I'll have to make even more bigger dilution refrigerators, and it's not so straightforward to think of this. So this was a careful choice based on the problems we had already solved, the fact that it was only 6 qubits, and we wanted modularity so that we don't get stuck with 1 qubit not working. Remember that Google's 53 qubit was actually a 54 qubit chip, but one of them didn't work. So if you really want a 54 qubit chip, then you have to throw that chip away. So here at least we can go back and swap that bad qubit out. So it was just a choice. So going forward with these new fab facilities, we will be able to create much more reliable chips of the conventional kind. But the ring idea is scalable. You can do this in a chip scale as well, and there are experiments ongoing in our lab. But it's still in early days in terms of figuring out the various challenges for this always connected architecture.
Okay,
There's a poster by one of my students here. You can go check it out.
Thanks.
So thank you, Vijay, for a wonderful talk.
Thank you.